The next lab we do is making electricity, and basically what we do with this is we have a moving or changing magnetic field that creates electricity, and we call that induction. Now this is kind of the other way of what we were talking about before. We use electricity to create magnetism. Now we're using magnetism to create electricity. Now if you put a magnet inside of a coil of wire and just let it sit there, it's not going to create any electricity, but if you actually move the magnet back and forth, then that'll create electricity. And we use a magnet moving inside of a solenoid. A solenoid is basically a coil of wire, and that's pretty much all it really is. But in that connection, you have a magnet that's moving, and it doesn't really have to be a permanent magnet. You can actually have an electromagnet, because a changing magnetic field, whether it's from a permanent magnet or electromagnet, will create electricity in the coil.
In this demonstration, we're going to create electricity. Now, to help us, we're going to use this galvanometer. The purpose of a galvanometer is two things. Basically, to show us how much current is flowing, as well as whether it's going in one direction or the other. We'll say this direction is positive, this direction is negative. The other thing I have here is a solenoid. A solenoid essentially is just one big coil of wire. Now, this whole thing just looks like something other than that, but really the wire starts here, wraps around many times, and then ends over here with two connections. And that's really all it is, just two connections to this big coil of wire. Now we're going to connect this coil of wire to the galvanometer in order to see, create basically a full circuit. But the galvanometer and the coil of wire do not have a power supply themselves. It's just basically one big loop as it goes through. Now here we have a magnet. This magnet has a north and a south end, and I want to show you what happens when we create electricity. Now first of all, you'll notice when the north end goes in, we create electricity. But I also want you to notice that as it's sitting here, there's no electricity created. It has to be moving. And you notice the north going in creates a positive current, and the north coming out creates a negative current. If we flip it around with the south end going in creates a negative current, and then the south end coming out creates a positive current. And you'll notice, so the direction of the magnetic field determines what direction the current is going to be created. Now, one thing to note is with the magnet just sitting in there, there is no current that's created. The main idea behind that is you have to have a changing magnetic field. So the presence of a magnetic field inside of here doesn't create current, but that magnetic field changing does create a current. Now, what you may notice is that the current is going back and forth as this magnet goes up and down. Now, with that being said, basically with going back and forth current, we call that an alternating current. And this process of having a magnet moving in and out of a coil is basically what we use in order to create all electricity. Now, when we get to create electricity for like your house and to use in order to power your computers or your TV or anything like that, you have to have a huge magnetic field in order to do that. So eventually it becomes to a point where moving the magnet is just not that easy. So it's actually easier to move the coil. Now with a big magnetic field, you can get a lot of current created. Now this is just a little bit of current just because of the structure of this, but you can move the coil around the magnetic field, and that will create a current as well. One important thing I want to say about this is it's not necessary really to have a magnet. The magnet is not the important part. The important part of the process is the magnetic field that the magnet has. And you may say, well, how do you have a magnetic field without a magnet? You have what's called an electromagnet. So here we have a nail with a coil wrapped around it. I've got it hooked up to the power supply. So if I move this electromagnet within the coil itself, that creates current as well. Now obviously the current is not as strong as it is with that magnet over there, because that magnet is a lot better than this electromagnet, but you can see that the current is created inside of the galvanometer due to the changing magnetic field. Again, if it just sits in here, there's no current that's created because there's no changing magnetic field. But once I move it back and forth, that creates the current. So essentially what we have is we have electricity creating magnetism, and then magnetism creating electricity. So that's the interrelationship between electricity and magnetism, is that you have electricity creates magnetism, and then changing magnetism can create electricity as well.
So here we have basically the same setup. We got this coil of wire and a permanent magnetic field, except this time, instead of attaching an electrical current to it, we're going to actually turn the coil inside the magnetic field. Now before, with the electrical current, that was creating a magnetic field that tried to align with the magnetic field that was here. In this one, we have a coil that we're changing in the magnetic field, and that creates electricity. So the energy goes the opposite direction. So the electrical generator converts mechanical energy back to electrical energy. I'm going to use that as the definition for a generator, converting mechanical energy to electrical energy. You notice the opposite there. The opposite direction that the energy goes with a motor, it goes from electrical to mechanical. For a generator, it goes from mechanical to electrical. All right, so credit cards actually use this, and basically credit card strips have little magnets in it, and those magnets are swiped by a reader, and that reader is essentially an electromagnet. And when the magnetism of the credit card goes by, it creates a magnetic field inside of that electromagnet, which creates a current that flows in one direction. Well, if you have a north end that's facing the electromagnet, then you're going to create a current going one direction. If you have a south end, then you're going to have a current going the other direction. If you remember, ones and zeros are associated with norths and souths. So basically, that north pointed one way is a 1, and then the south pointed the same direction is going to be a 0. And the current that's created is going to go one direction or another, which gives you basically reproduces your ones and zeros, and that lets the reader identify what the credit card number is using magnetism. So electric generators basically, they convert mechanical energy over to electrical energy. So in order to generate electrical energy, you got to start with some sort of mechanical energy. You'll notice in this diagram right here, we have a turbine with a generator, and that is basically the portion that we've been looking at for this unit, where we convert mechanical energy over to electrical energy. Now the key part to making an electric generator is that you have to have some way for that energy to be transferred. So you have to have something that transfers that energy. For example, in this one, we talked about a nuclear power plant. This nuclear power plant, basically what it does is it heats up water, boils that water, and then sends that steam over here. That steam then condenses and then falls over what we call a turbine. A turbine is basically a big paddle wheel or a big fan that either water or steam or air flows over, and then when it moves over that paddle wheel, it causes it to turn, and causing that to turn will cause the coil inside the magnetic field to rotate as well, and that is what generates electricity. Now for this power plant, the steam then converts over to liquid. That liquid then comes down and then it gets recycled back through. Basically any power plant that we have these days, most of them operate on this circumstance. The only difference between each power plant is how do we heat that water up. In a coal power plant, basically you burn coal, and that coal burning will heat up the water. This can also be used for a windmill. A windmill, you basically take a huge fan blade and put it at the end of this instead of all this construction right here, and that fan blade has air flowing over it. That air flowing over it will cause the coil to turn inside the magnetic field. If you stick this paddle wheel under, let's say, a waterfall or something like that, or even build up a very big wall in front of in the way of a river, and then let that water flow over this paddle wheel. And that's exactly what a hydroelectric dam does, is that it builds up that water, lets it get higher and higher, and then that water falls over the paddle wheel, generating mechanical energy that converts over to electrical energy. So to review the relationship between electricity and magnetism, moving charges or electricity, that creates a magnetic field, and we use our electromagnet for that. Moving or changing magnetic fields will create electricity, and we call that induction, and we use our magnet inside of a solenoid to represent that. So we have our setup here, a coil inside of a magnetic field. If we hook up electricity to it, then by hooking up electricity, it's going to cause that coil to turn inside the magnetic field, because it's trying to align its magnetic field that's being created. And if we take the same device, and instead of hooking up electrical current, we actually turn the coil inside the magnetic field, then it's going to generate electricity, so you get mechanical energy converted into electrical energy.
What I have here is a device that's called a hand crank generator. The reason it's called a hand crank generator because it takes mechanical energy that puts into it and then gets electrical energy out of it. Just to show you an example of this, I have a light bulb. If I connect this light bulb to the electrical circuit and I crank the generator, you see that it produces light. Now notice the more I crank it, the brighter the light bulb gets. And that's basically because of a conservation of energy. The energy I put into it here that converts over to electrical gets put into the electrical energy that lights the light bulb. Now what's interesting about this device is not only can it take mechanical energy and convert over to electric, but it can also take electrical energy and convert over to mechanic. So if I were to connect this to the positive end and then this to the negative end, you can see that the device will actually seem to come alive because the electrical energy then goes over to mechanic. Now notice, it's the exact same device. It's the exact same device either way. That if I put in the mechanical energy, I get electrical energy out of it that lights the light bulb. But then if I put electrical energy into it, that electrical energy will give mechanical energy out. So in one respect, with mechanical energy converted over to electric, that makes this a generator. But with the electrical energy converted over to mechanic, that makes this a motor. Now what gets really fun is if I take two hand crank generators and I connect them together. So if I put mechanical energy into this one, then it'll convert over to electric, and that makes this a generator. But then that electrical energy comes over here and gets converted over to mechanic. That makes this a motor. Again, the exact same device. And as a matter of fact, I can switch. I can make this now my generator and that my motor. So really the only difference between what we call a generator and what we call a motor is how the energy flows. When it goes from mechanical to electrical, we call that a generator. When it goes from electrical to mechanical, we call that a motor. So here we have what's called an electric motor. Now this electric motor essentially has two parts, and you'll see it's going here. I'm going to go ahead and disconnect it, and I'll show you the two parts. So you got the electricity coming in here, and then the electricity goes to one part goes to here, this coil down here, all right, down on the bottom, and then you have a coil right here as well. So you got two coils. Now one coil is able to be turned. And that's important because what that does is that allows for the motor to be able to produce motion. But this coil down here doesn't go anywhere. And basically what this coil does is it acts as a permanent magnet, in that the permanent magnet creates a magnetic north pole and a magnetic south pole. And then inside of that magnetic field between the north and the south is this other coil, and that's important because what that's going to do is this coil is going to create a magnetic field also, but that magnetic field wants to align with a magnetic field that's already there. So you got two magnetic fields that are trying to align with each other. Now the reason this continues to turn is because it tries to align with a magnetic field that's there, but then the magnetic field of this inner coil will switch. Now how does that happen? All right, so right here what we have is we have this wire, kind of hard to see, but you have these two wires. You'll see this wire right here, this wire right here. Those two wires are wires that one goes on one side and connects to this wire on the coil, and then the second wire over here connects to this side of the coil. But what you'll notice is as this coil turns, those connections will switch. So when the connections switch, that means the magnetic field of this coil right here will switch as well. So if the magnetic field of this coil switches as it's trying to align, then that magnetic field flips and then it tries to align again. But you'll notice as it goes around, it'll continue to switch its connection, which switches the magnetic field. So you get this perpetual motion of this object trying to align its magnetic field, then the current switches, so then it tries to align its magnetic field again, and then the current switches and then it tries to align its magnetic field again, and then it continues doing that because the current is always switching back and forth. All right, so what you're going to see, I'm going to show you actually when I connect this back. And you're going to see as it turns, all right, I'm going to turn the light out so you can see this. But you see this spark right here. And that spark shows the connection. Let me turn the light back on. Oh, keep going. And that spark shows the connection on this side where this coil is hitting that connection. So you got the current flowing through, and this is how you create a motor. Now you can do a lot with this. You can put an axle on here, you can put wheels on the side, you can attach a gear to this to run a motor or anything, the engine of a car. If you have an electric car, then you have the current coming in and causing this to rotate. And this is what produces our motion for our electric motors.